Alright guys, part 2 of the video. Won't take too long, hopefully. All we're going to be doing is cleaning up this maths and then translating our shear force and bending moment diagram equations into an actual diagram. So let's clean this up. I got to finish this term here. It's going to be 0.3 x squared again, because 0.6 divided by 0.2 is 0.3, and it's going to be a subtract because there's a positive term on that side, so when we move it to the other side it's going to be a negative. 0.3 x squared. Alright, there we go. Alright, now we can collect these like terms here, add them up. 1.08 take 0.746. We have 0.334x there. Alright, so we have 0.334x, add 0.1865, take 0.3 x squared. So there's my final expression for the bending moment in segment 2 of the beam, and we're going to derive that to get V2. V2 equals d on dx of M2. When I derive a constant term, like this one here, it goes away. I derive that one, we're left with 0.334. And I derive that one, we're left with minus 0.6x. Okay. So there are my two terms. Again, I'm going to pause the video, transfer these up here, and we're going to get to work on our diagrams. Alright, so here are my expressions up here for both segments of the beam. They're the only two segments that we have to figure this out for. So we're pretty much done there. All we have to do is construct the actual diagrams themselves, and that takes a little bit of wangling. So I'm going to clear up some space there, and here we go. So I'm going to draw these right beneath my actual beam, because this is how you will probably be doing it in your exam. You'll be doing it with a ruler, and you'll be doing it with more care than I'm doing right here. Much more care than that. Okay. So here is going to be my shear force diagram, and here's going to be my bending moment diagram. Now all we have to do, I'm going to do it in red, is we have to come up with where we're starting from. Now for the shear force, it's going to be the value of your reaction here, because immediately this will bump up our shear force to that value. We know this from experience, and we can also validate it with our expression here. If we plug in a 0 value to that x term, it's going to be 1.08 take 0, so we're going to be left with 1.08. So immediately we're bumped up to 1.08. There it is. So at the very start, that's where we are. And it's going to drop in a linear fashion, if we look at that expression there, up until the value of that point load. Okay, so let's plug in the end of this region here, the segment, because we know it's going to be dropping in a linear way until then. So let's get the two ends and we'll connect them with a line. So what is the value of V1 at the end of that segment? Well, we have to plug in the length, the overall length of that segment, or the length until the end of that segment, into this expression here. Okay, so in that expression, I'm going to plug in 0.25 meters as my x value, and we'll see what we drop down to. 1.08 take 0.6 times 0.25, 0.93. Okay, so it's going to drop into not too much, just a 0.93 here. 0.93. 0.3. And that's going to be right there in line. Notice how I'm lining these things up. There it is. Now we should be in the exam marking the x-axis like this. I'll do it here as well. 0.25. So this will be x here in meters. This will also be x in meters. And we can label these with kilonewtons here and m as kilonewton per meter. Okay, I hope I've left myself enough room there. Now, again, on paper, this is much easier to set out, so you should be fine. Do it properly, do it better than I have, and you'll be good. All right, so a straight line between these two. Guess I can do that with an actual line. Doink. There we go. All right, now, intuitively, you should know that this point load is going to be dropping down the value of the shear force, the value of that point load. And we will get to see that because in V2, because we've already done our V1 section for the for the shear force. So, but let's continue the shear force diagram. Here's my expression for segment 2. Again, I'm going to plug in the start of the segment where this actually is useful, and that is at the same value that this ended. So this goes until 0.25. This works from 0.25 onwards. So let's plug in 0.25 to begin with, and we'll see where we start, where V2 actually starts. So we got 0.334, take 0.6 times 0.25, 0.184. So we're dropping down to there, and it's going to be 0. We'll call it 18, and that is again in line with that point load. There we go. Okay, now this is going to stay consistent. This rule works till the end of the beam, and it's going to be a linear drop until there. So let's find out what it is at the very end of the beam, and we can draw a straight line between those 2 points. So here it is at the end of the beam. It's going to be 0.334. In this expression, I'm plugging in the length of the beam, which is 0.9. So take 0.6 times 0.9 minus 2.06. So it's going to go to minus 0.206. 206. Forgive the lack of room here. So there we go. That will go until that point there. We draw a straight line between them. And we could go ahead and come up with a new expression for segment 3 to figure out where RBY takes us, but intuitively we know that it takes us back up to 0 because, well, let's look at this. This is 0.206, this is 0.207. Obviously there's been a little bit of a rounding error, but these two, if we add them up, they go to 0. So we go straight back up to 0 again. There's my shear force and bending moment diagram. Well, my shear force diagram done. Onto bending moments. Same thing. M1 though always starts at 0, and we can see that because if we plug 0 into X here, we're going to get 1.08 times 0, 0.3 times 0, which is 0. So we start at 0 always with M. Now let's figure out where it's going to be at the end of segment 2. So we're going to plug in 0.25 meters, the end of segment 1, because that 0.25 meters represents the end of segment 1. So we're going to plug that into our first bending moment equation here. So we got 1.08 times 0.25, which is the end of the segment. Take 0.3 times 0.25 times 0.25, or 0.25x squared, same thing. 0.25 squared. 0.251. Okay, so let's put that in. 0.251. We'll call it 0.25. That goes to 0.25 at the end of segment 1, which is where the point load acts, which is right here. There we go. Now, I know, and you should know this as well, because this is going to be a continuous line, not like this, it doesn't bump down with the value of the point load. It's going to start a new curve at the same point. I don't have to calculate M at the beginning of the segment because I know it's going to be the same. If I wasn't pushed for time here, I'd plug the numbers in and show you. But if we put in 0.25 into this equation here, it would also equal 0.25. Okay, so now all we really have to do is figure out what M2 is at the end of the beam, and then we might have to do a little more, but we'll see. Well, we know actually M2 at the end of the beam is going to be 0 again. So we're going to curve back down to there. All right, so we could say it's going to curve up to here because we know it's going to be a quadratic. We can just draw a curve in. Then we can draw a similar curve back down here. But we need to know where the maximum is. And the way you find that out is actually where your shear force crosses the x-axis is where your maximum is going to be. So if you don't actually want to plug in anything, try and derive this and then put it to 0, you can see it actually, because actually to find the maximum of a turning point, you actually derive the value of the function and then equate it to 0. Well, we know the derivative of our bending moment is our shear force, and we know where that hits 0 because it's shown on the diagram. So it crosses somewhere here. Well, we should actually find out exactly where that is. So we know that that's in V2. So let's quickly see what x has to be when V2 equals 0. So V2 equals 0.334, take 0.6x. When that equals 0, we got this. 0 equals that. So 0.6x. I'm rushing through this, sorry guys. Don't have much time left on the recording. So x has to be 0.334 divided by 0.6. 0.56, we'll call it. 0.56. So this goes up to about double 0.56. That says 0.56, guys, just pretend. And it's going to be right in line with that. Well, sorry, x is at 0.56, excuse me. X is at 0.56, so we have to plug that number in to, so 0.56 is going to be somewhere around here. I know it doesn't look it, but it's going to be somewhere around here. 0.56, 0.56 is there. So we have to plug that into M2 to find out what we get. I'm just going to pause it and do that calculation to save some time. So there's my calculation. It's 0.28 roughly kilonewtons per meter at that 0.56 meter mark there when I plug that into this equation to find my maximum. It's 0.28. So this is not 0.56 here. It's 0.28. So my curve is going to go up until there, and it's going to go up until 0.28 and then drop back down. So it's going to look something like that. Okay, guys, that's it. I hope that helped. Good luck on your test. Much love. Goodbye. I apologize for being sick, but there you are. Bye, guys.